Okay, welcome back. This is Year 10 Physics. We are talking today about electricity and we're talking specifically about series and parallel circuits. All right, our aims today. We're going to look at how current flows in a series circuit and in a parallel circuit. Now specifically we want to be able to calculate the resistance, current and voltage in different components of a series and parallel circuit, as well as the total resistance, current or voltage of a circuit. We're going to start on that one today. So in a series circuit, there's only one path through which the current can flow. It is a continuous loop from the battery around through the circuit and back to the battery. So think of a battery like this, around through some sort of resistor or component, and then back. There's literally only one way for the current to flow. The electrons will go around this direction, and the current, which we refer to as the conventional current, has got to go around that way. Yes, I know it doesn't make sense, and conventional current doesn't actually flow, but it's what we always talk about. So the current flows through every circuit in the element. I've shown one resistor there. Perhaps if there was another one in here as well, the current would go through the first one, then the second one in sequence, in the series. The voltage supplied by the power source is used up by all the components in the circuit. So the voltage from our battery has got to be used between those two resistors in that circuit. The voltage drop across each element or each resistor or each component of the circuit is a function of its resistance and the current flow in the circuit. A few rules for us. In a series circuit, the current is constant. The current is the same everywhere because it's coming out of the battery, because it's caused by the voltage of the battery. So it is literally the same current flowing like a pipe all the way with water through it, all the way throughout the circuit. The voltage is the energy, it's the potential energy that causes those electrons to flow, which is the current, and that's got to be shared between each component of the circuit. So the voltage, the supply voltage that comes from the battery, is the voltage drop across each component within the circuit. The resistances of any resistors or components in the circuit simply add up because it all compounds together as we go around the circuit. So we literally just add up all the resistances in a series circuit, which is fairly straightforward. Here's an example. So we've got a battery there with 12 volts. We've got 3 different resistors in our circuit there. We're showing our resistors as the little squiggly lines. What are we going to do? We're going to find out the current flowing in the circuit and the voltage across each of those resistors. So just have a think about how we might solve this. Don't just listen to the video blindly. Think ahead and think, what am I going to do? The only formula we've discussed is V equals IR. So that's obviously the one we're going to use. We want to know the current flowing through the circuit initially. So it's a function of V equals IR. We have a voltage, but we need to know the total resistance to put into that one. So we're going to use V equals IR to find the total current in the circuit, but we've got to find the resistance of each resistor first. And as we just said, in a series circuit, we just add the resistances together. So the first resistor is 10 ohms, 5 ohms, 9 ohms, 24 ohms is the total resistance in this circuit. So we've just worked out that the total resistance in this whole circuit is 24 ohms. So what it means is we can effectively think of these 3 separate resistors as acting like they're one 24 ohm resistor. And that's how the top diagram becomes the bottom one. It's kind of a way of thinking about it and simplifying our circuit. We now have one resistor, one voltage. Finding the current with V equals IR is a fairly straightforward process. So knowing we have 24 ohms resistance, knowing we have 12 volts, we just put in V equals IR, we rearrange our formula, plug our numbers in there, and we get half an amp. 12 volts divided by 24 ohms is 0.5 amps. Fairly straightforward. That is the current. Half an amp is flowing through every single component in this circuit, out of one side of the battery and back into the other. Okay, let's move on to part 2. The voltage drop across each resistor. So what we know is that the current in the total circuit current going through every component is 0.5 amp. So each resistor has 0.5 amp going through it. We know the resistance of each resistor, that's listed there. So V equals IR will tell us the voltage from this total 12 volts that's split up between each one. So how much of that potential energy is split between each one. So very straightforward, V equals IR. Look at our first one here over on the left. My current is 0.5 amp because that's the total circuit current. My resistance, 10 ohms, 0.5 times 10 is 5 volts. And same with the other two. We have 0.5 amp times 5 ohms because it was 5 ohms up here, 2.5 volts. And we have 0.5 amp times 9 ohms, 9 ohms there, 4.5 volts. So that is like the measure of the potential energy taken up by each resistor in this circuit. Now, we should check that we're right. So that last little bit of red writing down the bottom there, we check that the total voltage is all of those individual ones added together. So I have the 5 volts, 2.5, 4.5 listed in the middle here, and those three add up to 12 volts, which is what I originally started with in my battery, therefore it works. You can clearly see that if we'd have worked out resistance 1 and 2, we could have just subtracted those from the 12 volts to find the last one on resistor 3. It would work the same way. Okay, that is series circuits. Now, parallel circuits. Parallel circuits are slightly different. In parallel circuits, the parallel or a parallel section of a larger circuit, the current's got to split and travel down two different pathways. So think about this scenario here where I've got 5 amps coming in and there's a junction or a split or a node here, and 3 amps, for example, may go up one path. There was 5 to start with. That means 2 amps has got to go down the other one, but I end up with my 5 amps at the other side. So think of our analogy of the river. It's like the river branches into two different pathways, and the physical water molecules have got to be divided between each pathway of that river. But if the water comes back together again into one river again, then all those water molecules come back together. All the electrons come back together. The current afterwards has got to be the same as what we started with. This is actually known as Kirchhoff's current law, when essentially the current going into that branching section has got to equal the current going out. Okay, parallel circuits. So when we add resistors in a parallel circuit, the resistors kind of add together in these different arms of the circuit and give a bigger area for the electrons to physically flow through. So it's like it makes it easier for the current to go through compared to a series circuit. The total resistance is found by the sum of the reciprocals. What does that mean? It means that equation there in the red box. 1 over the total resistance is 1 over each individual resistor in the series, the resistance of each individual resistor. The reciprocal is just like that 1 over business. So here's my example here. Determine the total equivalent resistance for these 3 resistors shown. 10 ohms, 5 ohms, 9 ohms. Alright, first thing I'm going to do is I'm going to put down my formula. 1 over total resistance is 1 over each individual resistance. I have a 10 ohm resistor, so it will be 1 over 10 ohms. I have a 5 ohm resistor, 5 ohms, 9 ohm resistor, 1 over 9 ohms. From this point on, it's just middle school mathematics, or probably even primary school, where we're just adding fractions together. So 1 over 9 plus 1 over 5 plus 1 over 10. I want to find a common denominator, which is 90. So it's like this one got times by 10, so it's 10 over 90, and so on with the other ones. So I've got 10 over 90, 18 over 90, plus 9 over 90 down here. Add them together, 10 plus 18 plus 9 will give me 37 over 90. Do not stop at this point. This is a common error. You have not found the resistance, you have found 1 over the resistance, the reciprocal of the resistance, 1 over. So you need to flip that over the other way. So it's going to end up as 90 over 37. A way to write that mathematically, instead of writing 1 over the total resistance is to the power of -1. A negative indice means 1 over in mathematics. So we end up down here where we've got 90 over 37, and how many times does 37 go into 90? You may be able to use your calculator for that one. 2.43 ohms is our total resistance here. Okay, now that I've worked out that my total resistance is 2.43 amps from the previous slide, it's like these three resistors are all acting together like one big resistor. It's a way of simplifying the circuit just to sort of make it easier for us to see what's actually going on here. Right, that's resistance. Now voltage. The voltage drop across any component in a parallel circuit is equal. If the circuit is a parallel circuit and the voltage entirely parallel, then the voltage drop across each component is equal to the supply voltage from the battery. Let's go back and think about our river example. We've got a river. The vertical fall of the river is like the voltage in an electrical circuit. So if a river splits into two different arms, like a parallel circuit, the current splits between those two arms. It doesn't matter what happens if those two arms come back together at the same point. One could go really, really flat for a long time and then go over a massive waterfall, and one could just gently go down the hill all the way. But if they come back together at the bottom, the total vertical height change of that river is the same for both arms. That's our voltage. The voltage in two arms of a parallel circuit is going to be the same. So if it's an entirely parallel circuit, a battery into a parallel circuit and then back into the battery, then the voltage in each part of that, each arm or each pathway in the circuit is going to be the same. So knowing the total voltage, the current flowing through each resistor or each arm of the circuit can be then found through Ohm's law. It's basically the function of V divided by R. So we're rearranging Ohm's law into I equals V over R and using that. Let's have a look. Okay, so here's our example of our parallel circuit. And the question asks, determine the current flowing through the entire circuit. So the easy way to do this is if we know the combined resistance or the total resistance of each component of our circuit. That's what we need to understand. And that's what we worked out last time. So we know our voltage is 12 volts. That's written down there. We know our total resistance, 2.43 ohms from previously. Ohm's law will tell us I equals V over R. Plug my numbers in. 12 divided by 2.43 is 4.94 amps. Now that 4.94 amps is my current coming down the circuit. That would be the electron flow I've shown there. The actual current, conventional current, which doesn't exist, is down here. And that's going to be my 4.94. And that is going to split between the three arms of the circuit equally, or not necessarily equally, according to their resistances. And it's all going to combine back together over that point over the other side there. So let's have a look at that. Determine the current flowing in each resistor. We're going to use V equals IR to tell us this and see how we go. So in my first resistor, I've got 12 volts coming from the battery. I've got 10 ohms in that resistor because it tells me up there. 12 divided by 10 is 1.2 amps. And I'm going to put that in there over on the left. 1.2 amps. Second resistor, that's 5 ohms. So I'm literally swapping out this thing down here. 12 divided by 5, 2.4 amps. And I'll put him over on the left-hand side as well. I have both of them in there. Third resistor is 9 ohms. 9 ohms goes in there. 12 divided by 9 is around 1.34 amps. There's a little bit of rounding in there, but that's okay. So I've answered my question. I found all of my three currents going through those resistors. I can check to see that it adds up to the total. The total was 4.94 that I previously calculated, so all of them must add up to what that total is. And you can see my 4.94 total, and then the three that I calculated, which came from my three here that were calculated, and 4.94 equals 4.94. It's like the river flowing example. The river flows down the hill and is splitting into three parts, but it's coming back together over here. So over here near the asterisk, all of the water must come back together, so the current over there must be the same again. Okay? Your job now is to practice that. There's a worksheet there in the OneDrive that you can check out. Have a go. Make sure you practice the skill, get the idea of it, because our example is going to get more complex next time. So what have we done? We looked at our current flowing in series and parallel circuits and used it to calculate various elements of the circuit to have a go. All right. Well, really appreciate you all coming today. Thanks a lot. Hope you enjoyed it, and